Welcome back, everyone. In this video, I will be completing the section on linear approximation. And in the second half here, we're going to be talking about differentials. Now, differentials are an idea that's related very closely to linear approximation. So one of the things that's kind of inherent about it is since it's related to linear approximation, when we're talking about x values or anything like that, we're going to be thinking about things close to zero. Right, but by definition, the differential dy is of a function f, so I should specify we definitely need a function f, is given by dy equals f prime of x times dx. Now, one thing is that with linear approximations, we specified some a value to find the linear approximation from. When it comes to differentials, we're not specifying an x value. This is actually going to be a formula, as you'll see. We'll use the formula to figure out things using the differential. But what dx represents is the change in x, so it can be any real number, and di will represent the change in the y value of the linearization of f at some specified x value. But that's a lot of words, and while we saw tangent lines prior to this section, we've never talked about differentials, so I want to go ahead and draw a quick picture as far as what these are representing. Let's say we have a function, and for the purposes of this problem, it's always best to really draw this type of shape to see differentials the best. And I'll go ahead and say that x, the value we want to pretty much find this differential at, is right here. And then this over here would be f of x. Now it stems from tangent line. So I'm going to go ahead and just try to draw on a tangent line here. And this is my tangent line or linearization. And the idea is the following. Let's say you wanted to estimate a close value on your function. We'll call this x plus a. I don't know. Don't worry about it being related to the previous part about that a. But let's say we wanted to estimate this f of x plus a value. The idea is that the tangent line is going to be kind of close if a is kind of close. We saw that last time, but it's also going to tell us pretty much the furthest away it's going to be. So what I mean by that is if we kind of give this space in here from x to x plus a, yes, it's represented by a, because if you do x plus a minus x, you get a. If we call this dx, so this is the dx from above, then what's happening here is that if we look at the tangent line at its starting point, which matches the function value because it's the tangent line, and then at the ending point, what I'm going to do is draw a little triangle here. I'm not going to actually make it a triangle, so it's going to be dashed in. Dx is up here, so it's the same difference in x here. The dy is exactly the change in y. So the dy, kind of like how I wrote above, is the change in the y value of the linearization. Right, that's exactly what it's represented. Yeah, there's a lot of stuff going on because we have to have the tangent line already, but the point here is that we can use this dy to do something, and that something is actually to figure out a maximum error. So dy also gives you the maximum error. And this is an estimate because it is exactly what we're talking about above. We have this idea of being close. The idea of being close isn't very defined. So it's an estimated maximum error of the function f of x, the function's value rather, f of x plus a from the linearization. All right, so let me go ahead and quantify what I mean by this error. So what I mean here is that if you look at, I'm going to draw this same kind of tangent line, or sorry, triangle, but for the actual function itself and not the tangent line. Even though this is dx, it's the same change in x. For some reason, when we're talking about the function itself and not the tangent line, people like to use delta x. Delta just means change in. Sometimes you'll see people, instead of write x plus a, they'll write x plus delta x, which is fine. This is the change in y on the actual function is delta y. And delta y is represented by f of x plus a minus f of x. So really just to quantify all this here is what it's saying is that we want to estimate the largest delta y can be using the differential. And that was supposed to be a colon, but the largest delta y can be. Well, based on this picture, delta y is pretty much less than or equal to dy. Why? Well, because dy, the tangent line, is growing more than the function itself. Now, this does depend on the way it's drawn. I could have drawn it another way so it looks sort of like a parabola. Instead of going this way, it can go the other way. But the important thing you realize is when we're close, as long as dx is small, it's an estimate. So the largest delta y can be is dy, assuming delta x, which is the same as dx, is small. Now, we won't really talk about delta y and delta x specifically. We're just going to use the differential part. But the idea is if you can compute this differential, you pretty much know the maximum error of something. And I think the best thing to do is look at an example of a function where we don't easily evaluate the numbers, like an exponential function. Use the differential to find the maximum error and then actually do it in a word problem. So that's what we're going to do. I remember when I was learning this, this was one of the most confusing things. And then when I saw an example, it started to make a little bit of sense. So hopefully it'll do that for you as well. All right. And one thing I guess I can mention is that I said at the beginning, but I'll reiterate, we're not specifying x here. So when you compute the differential, you're basically just your differential dy equals, you do the derivative of your function and then you multiply it by dx. So that's all the differential is as an equation. You do the derivative and multiply by dx. All right. So number one here says, let y equals e to the x over 2 power. Compute the differential dy, then evaluate dy at x equals 0 with dx equals 0.05 and interpret the result. And I think even though this isn't necessarily a part of many problems and you won't be asked to do this in general, interpreting it will help bring clarity to what we did and what I was describing above. All right, so dy is f prime of x dx. All right, and we're given the equation y, but we know we can just think about this as f of x. So this means do the derivative of this and just multiply it by dx. Now I'm just going to do the derivative on the side because we know from past experience, no matter how messy or short a derivative is, it's best to just kind of do it by itself and then use it after we have our formula. All right, so the derivative of e to the x over 2, well, this is an exponential function, so it starts off being itself e to the x over 2, but then we multiply by the derivative of the exponent. The derivative of x over 2 is 1/2. And just to rearrange this, this equals 1/2 e to the x over 2. At this point, we've computed so many derivatives that this should be totally fine. And well, all our differential is dy. When you're asked to solve for dy, you pretty much got it. dy equals 1/2 e to the x over 2, so our derivative times dx. That's all the differential is as a formula. Now we want to understand what it is a little bit more than that, but at this point, let's just say you didn't really understand what I was talking about above, basically because what it's used for is to calculate estimates of errors. Well, at least we understand the formula. Well, now with this formula, we're told to do what? We're told to evaluate dy, so we want to figure out dy when x equals 0 and dx equals 0.05. Well, now this might make a lot more sense because if you look at our formula for dy, we have an x in it, so we can plug in x equals 0, and we have a dx in it. We can plug in 0.05. Now, one thing to keep in mind here is that when we're talking about dx, it has nothing to do with x itself. Dx is its own number. It's representing the change in x. So when we see dx, we don't say d of 0 or d times 0 or anything. Dx and x are completely separate. All right, so let's go ahead and do it. We have dy equals 1/2 e to the 0 over 2 times dx. And I guess I'm needing to actually plug this in to make it more sense. So we can just do both at once. We don't need to plug in x in one step and dx in the other. dx is 0.05. Now, one thing I want to point out here is also, what I was talking about before is that when this is coming from linearization. With linearization, we want to be close to the x value. Well, here we're told we want to be close to x equals 0. The only thing that's telling us we're close is that dx, this change in x, is close to 0. As long as this number is small, everything works. If you had dx equals 5, for example, this wouldn't make sense because it would be too big. But 0.05 is very small, and we're good. All right, so what do we have here? We have 1/2 e to the 0 power. Anything to 0 power is 1, up to a point. And then we have times 0.05. And if you compute this out, 0.05 divided by 2 is 0.025. All right, so what this is saying is that dy are differential at x equals 0 with dx equals 0.05 is 0.025. How do we interpret this? So hopefully this is where maybe it starts to come together. Interpretation. Pretty much what we figured out, we completely avoided actually computing the linearization because we didn't care to estimate. Let's say I didn't want to figure out what e to the 0.05 over 2 was. What I'm trying to figure out is how much of an error will I get from its original point. So what this is saying is that the maximum possible, but this is an important point, estimated error when evaluating f of 0.05. So where I'm getting that is I'm taking my x and I'm adding my dx to it. So just kind of go back to the picture real quick. Imagine if x was 0. Then if I take my dx and add it to it, I get 0 plus 0.05 is 0.05. And what this is saying is this dy should be bigger than my actual change in y. So it's saying the maximum possible error when evaluating f of 0.05 using differentials. This is the important thing, is we're using differentials. So the error can be different depending on what method you're using. We only know differentials, but we do need to specify that. Using differentials is 0.025. And I should say from x equals 0. All right, because that's our base point. That's basically where we would find the tangent line. Basically what we did, just to reiterate again, if we found the tangent line or the linear approximation at x equals 0, then we plugged in 0.05 for x. So kind of going way back to the first problem here, if we figured this entire equation out, plugged in 0.05 and got a number, we saw that our error for this one was really close. Well, we expect that our error for this one, we don't know what it is because we're not actually doing the linear approximation, but we know that it should be no bigger than 0.025. That's what the differential is saying. Now, just like at the beginning where I showed you the graph of the function, it was a parabola at the beginning and the tangent line just to show you it's close. I want to talk more specifically just for a moment about the differential here. So what I've gone ahead and done is, this is our function. If you figure out the linearization at x equals 0, and use the formula above. So the way we were doing it in the last video, you will get this equation. Now let me go ahead and zoom in because it's at x equals 0. I'm zooming in. And what we want to remember is that we only care about being 0.05 away. So notice that this is 0.2. And if you kind of realize what it's doing here, we can keep zooming in. This is 0.1. If I zoom in a little bit further, this is 0.05. Now what this is saying here is that our maximum error, if we were to completely just avoid this equation. So I wanted to plug in on the y equation here. This one is, I'm on the green, so it's highlighted. If I wanted to figure out 0.05, well, its actual value, if I plug it in for x here, 0.05, I get 1.0251. Well, if I go to my linearization and now I see what 0.05 is, I get that 1.025. Well, where is this number coming from? It's coming from the fact that when you plugged in 0, you get 1. And then when we plug in the 0.05, you get 1.025. And if you subtract them, you get the 0.025. So what it's saying is we expect the maximum error to be this from our linearization. Now, once again, this is just a reasonable guess because it is an estimate, so it's not absolutely 100% correct. Notice that when I go back here and I look at the 0.05, it is slightly more than 1.025. The error then is slightly more than 0.025, but it's only off by the 4th decimal spot. So it's 1.0253. So one thing I want to really stress here is that the word estimate is thrown around for a reason. But as long as you're very close to your base point, which means your dx is small, then your error is going to be pretty good error estimate. All right. So once again, this is just giving us really the change in the tangent line equation. Its y value, the 0.025 from here. We're just completely avoided actually computing the tangent line, and all we did was compute the derivative and multiply it by the change or the delta x or the dx. Right, but that's exactly what the tangent line says. If the slope here was 1 and we went up by 1 as well, I'm throwing out different numbers here, then if x increases by 1 and the slope is 1, then y also increases by 1. So that's pretty much what it's doing. All right. So what we're going to do is go ahead and now use this in a way where it would be more realistic. So, there could be a reason why this function e to the x over 2 is important, but realistically what you're going to do if you ever have to use differentials in some application is going to be like this. So it says the edge of a cube was found to be 15 centimeters. I'm going to go ahead and highlight cube because you can read from the question here that we don't have a formula. So the edge of a cube was found to be 15 centimeters with a possible error estimate in measurement of 0.4 centimeters. Well, without reading the rest of the problem, what I already know is that we're talking about a cube. Let's say x is the edge length of the cube. You can give it any name you want because we're not told what letters to use. We can use it on our own. So this is the edge length of a cube. And what we're told is that it was found to be 15 centimeters with a possible error in measurement of up to 0.4 centimeters. Of course, anytime you measure anything by hand, you can have an error. Well, what's this possible error representing? This is the dx, because it can be up to 0.4 centimeters away. So dx, when we compute our differential, will be 0.4 centimeters. Now we know from dealing with units and equations before, we're just going to use the numbers here, but I want to keep track of our units. What it says is use differentials to estimate the maximum possible error, the relative error, and the percent error in computing the surface area. So we're not talking about the volume of the cube, we're talking about the surface area of the cube. So keep that in mind. Very often with three-dimensional things, we always want to use the volume, but this one says use the surface area. Well, the main thing here is that you have your x, you have your dx. We read them away. And if you compare to the problem up here, we were given our x and dx, and we were given the function. Well, we just need to come up with the function, but the function f of x, that's going to be the surface area of a cube. And if you're, once again, if you're not familiar with these formulas, just look them up. This is going to be 6x squared. The way to remember that, if you do want to help yourself remembering that, is that the cube is just, a cube surface is 6 squares. The area of a square is x squared because we're using x as the length, and we have 6 of them, so it's 6x squared. All right, but what is the differential formula? The differential formula, dy, because that's what we're going to use to compute, equals f prime of x dx. Well, we know what x is. We definitely need f prime, and we're pretty much following the same steps as above. And then we're going to multiply it by dx. Okay, so what are we dealing with here? We've got f of x equals this. We need f prime of x. Well, let's go ahead and do that. F prime of x, well, this is just x, so just a normal power rule will give us 12x. Nothing challenging about that derivative, thankfully. And now the formula for dx, if we go ahead, or sorry, dy, the differential, if we plug that in, we get dy equals 12x dx. Okay. All right. And I'm just trying to draw parallels to the above problem we did. We have our formula for dy. We want to estimate the maximum possible error. Remember, that's exactly what dy gives you. If we plug in our x is 15 and our dx is 0.4, we will get the maximum possible error. And that's what we want to start with. And once again, I'll just reiterate over and over again, it's an estimated maximal possible error. So the maximum possible error, what is it? Well, we take our dy formula, our differential, and we plug in x is 15, so we get 12 times 15 times dx, which is 0.4. Now, because this problem says round to 4 decimal places, we can just go ahead and plug it in, not even worry about trying to do this by hand. So let's do that. 12 times 15 times 0.4. No, we get a nice whole number. It's 72. And now if you want to keep track of your units, because we're talking about an area, it is a surface area, but it's still an area. It's squared units, so it's centimeters squared. Now the next couple things that we want to do, the relative error and percent error, we haven't really talked about, but there's a quick formula for relative error. Go ahead and write it down. It's just the maximum possible error, what we did in the first part, divided by the actual quantity itself. We're talking about the surface area, and we want to talk about the surface area at the given number we measured, which is 15. So actual surface area. Now, if you're dealing with volume, it would of course be actual volume. If you're dealing with area of like a circle or a square, perimeter, anything like that, it's just the actual function's value. So in the above part, we figured out the maximum possible error is 72. If you include the units here, you'll notice that they'll cancel out. Now the actual surface area, well, our function or the surface area formula for a cube was 6x squared, and x is 15. So if we plug in that, actual surface area, f of 15 equals 6 times 15 squared. And it's kind of a big number, so let's go ahead and just plug it in. We know it'll be a whole number, so not too bad to actually do this. 1,350. So the actual surface area is 1,350. It's also centimeters squared because we're talking about area. So those completely go away, which means this actually makes sense. Relative error should not have a unit. It's just asking you, how off am I relative to my actual area, surface area? So I take the numbers and I divide them. 72 divided by 1,350 And because I want decimals, I want to interpret this. Let me go ahead and press enter. And it says round to 4 decimal places, 0.0533, 0.0533. So the relative error is 0.0533. Now, as far as just reading this off, it's maybe not that useful, but the percent error is more interpretable usually, or percentage error. All it is, it's you take the relative error and you convert it to a percent. And, you know, you either multiply by 100, move the decimal place over, but all we're doing is converting the relative error to a percentage. So whatever you want to do, just move the decimal place over twice. One thing I'll say is that because we want all of these to 4 decimal places, if you move this over twice, you get 5.3333 forever. So it's 5.3333. If you only move it over twice in here, it looks like it's 5.33, and that's not the 4 spots. So 5.3333%. Now I think if you understand what relative error means, this is very helpful, because what this is saying is that, you know, imagine you're making cubes because you're actually, maybe you're in a company that's creating boxes and you're designing something. You want to know how much material you're using to make the surface of this cube, this box. Well, if you're off by up to 5%, which is what this is saying, you could be off by up to 5%. Well, what this is saying is that you could be using 5% more material, which is 5% more money on every box. And that would be a big deal. So this relative error, this estimation of 0.4 centimeters is pretty big relative to the 15 you actually measured. Now, if this was 100 centimeters and this was 0.4, then this would be a lot smaller, because the relative error in your measurement is much smaller. But you would just go through and do this problem with 15 f for x instead of 100, and you would come up with a much smaller number here at the end. All right, but that is the section on differentials and linear approximation. I hope this last example kind of helped you realize maybe what differentials are used for at this point. They are used for computing errors, and in general, it's a lot easier to compute an error just by using this formula than trying to actually compute, because you might not know, dealing with a function, how to actually compute something that's not there. Right? A measurement that's never been taken, so you can't actually plug it in. You have to estimate a potential error. That's what this is used for. But I'll see you in the next video.